Hello everybody. Now last class we were discussing about the different kind of the metal transfer mechanism associated with the gas metal arc welding process. So objective was to analyze this kind of metal transfer thing is basically for the development of kind of metallic printer or we can say that kind of additive manufacturing technology. So some sort of understanding of the different kind of the metal transfer is required. Now we try to look into the different aspect say what we can develop the model the metal transfer model that is actually very much focused to the gas metal arc welding process or maybe we can say that exclusively gas metal arc welding process, not the other welding process associated with some kind of the metal transfer. So, you know this metal transfer mechanism is actually very much complex in nature, and the development of all the physical phenomena occurring during this particular process, it is very difficult to develop one model. Rather we can look into the different aspect, physical aspect associated with this during the metal transfer part, and then how we can model them looking into the dividing the different zone, and accordingly we can make some kind of the modeling approaches we can follow, that we will try to discuss here. So, before doing that, some overall idea that how this metal transfer is normally happen in gas metal arc welding process. So, it is a simple way we can represent this thing. There is a continuous feeding of the wire arc. So, continuous feeding of the wire, and there is a generation of the arc, and then basically it follows some kind of the feed rate. So, this feed rate is continuous in that assuming that is a continuously, and that particular phenomenon we try to capture to develop develop the model in terms of the what are the temperature distribution, what are the flow field associated with the either the metallic component or either in the case of the within the arc also, and even within the field that shielding gas flow rate or flow field is possible to estimate using the modeling approach. So, definitely once we look into this thermal analysis and this material flow in this particular cases, we have to solve, we know that governing equation, particular governing equation along with the interface capture or basically interface methodology has to be look into this thing for the development of the model. Now, material deposition rate, simply we can estimate the deposition rate m dot equal to the efficiency term is there, you can see this is the efficiency term, and the density of the material, and the cross sectional area. Cross section area means normally you can estimate the what is the deposition rate which in terms of the volume flow rate or in terms of the mass flow rate. Now, when you try to look into this mass flow rate or volume flow rate, in this cases first we try to look into the volume flow rate, then the velocities, suppose feed velocity is particular direction is this one. So, or maybe you can say that f is the feed velocity, feed in the particular direction, but normal to that direction what is the cross section area, that has to be considered here. So, this cross section area assuming the diameter of the wire is d, small d. So, cross section area equal to pi by 4 d square. So, then cross A equal to pi by 4 d square. Now, if we assume the feed rate of the electrode is some in unit is say millimeter per second, and diameter is the length, basically in terms of the diameter of the electrode, the length unit, that is millimeter in this case, and for example density of the material is this. Now, we know A into F. So, that indicates basically millimeter square into millimeter per second. So, it is basically millimeter cube per second. So, this is the volume flow rate. So, volume flow rate, when you multiply by this density, then it becomes mass flow rate. So, density for example here say kg per millimeter cube. So, it becomes kg per second. So, this is the mass flow rate, simple calculation we can do, but we can use the solid wire efficiency term because in this case there may be some kind of the we can loss we can account here also, and that in terms of the efficiency. Now, we have already discussed that this is the globular kind of the metal transfer may happen, and short circuit metal transfer may happen, spray transfer happen, but of course whatever metal transfer mechanism is involved, it is always that we try to keep that there is a continuous feeding of the wire. So, continuous feeding of the wire, but mechanism of the metal transfer can be different. It can be globular kind of transfer, it can be short circuit transfer, it can be the spray transfer also, or even it can be the pulse spray transfer kind of the metal transfer mechanism may involve. Now of course, this metal transfer all actually influenced by the what are the different parameters we use in these cases, and what are the power source characteristic, is a continuous or pulse, all these cases the metal deposition rate depends on that. Even if we try to handle the, for example, there is a pulse current supply in case of the gas metal arc welding process. So, in that cases everything we can do all this calculation based on the average power. So, if based on the average power we can estimate what is the average power, because average power is equivalent, even if it is a pulse condition also the average power is equivalent to the continuous mode of current. So, therefore, for a pulse current application we can estimate the average current, and based on the average current we can estimate all these kind of parameters, all this calculation deposition rate can be done in case of pulse current rate. So, apart from this thing, what can be the modeling approach? So, already mentioned this thing that transfer mechanism can be different, but this transfer mechanism can normally, most of the cases we can estimate, we can find some kind of the critical condition such that it decides the whether the metal transfer mechanism follow some sort of the globular kind of the transfer or short circuit, or in kind of the spray kind of the transfer normally happens, but that condition has to be developed looking into this thing. But if we assume there is a some kind of in general we are talking about even any kind of the metal transfer mechanism in general, it is simply we can assume there is a droplet transfer from where, and then this droplet is transferred, the creation of the droplet, and then this droplet is transported through the creation of the arc in the field of the arc, through the creation of the arc, and then droplet becomes finally part of the molten pool. So, it actually mixed to the with the molten workpiece in this particular case. Now, point is that if there is a continuous feed rate, then in the modeling approach we assume the continuous feed rate and there is a continuous development of the supply of the droplet. So, it is like that only we can put the condition that say for a particular situation or per unit time, maybe particular certain time, the phenomena is something like that. There is a, this zone is held constant between the electrode and workpiece, and there is a continuous supply and there is a continuous melting or creation of the droplet from the electrode tip, and such that the gap is maintained as a constant. Assuming this thing, and there is a arc is created between the electrode and the workpiece, and in between the droplet is transported from electrode to the workpiece, and then this can be considered say this phenomenon is happening over with certain frequency. So, within certain frequency means then we have to look into the cycle time. So, we look into one cycle time, and one cycle time there is a one droplet is transported from electrode to this arc, this phenomena. But at the same time maybe before transported from electrode to the workpiece material, there may be the possibility of the creation of the another droplet on the electrode. So, this phenomena we try to make the model. Now, this holding force, we know the electromagnetic force, gravitational force, plasma drag force is also there, because this plasma, this arc is created. So, we can say this actually associated with some kind of the plasma drag force. Now, since it is a symmetry kind of phenomenon, if we assume this thing, say the basically electrode is normal to the workpiece. So, in that situation we can assume this is the symmetric problem. So, symmetric problem only half of the domain we can consider for the analysis. Now, this holding force and maybe this there is a one thing is that first is the what we can set some criteria at this point, that what kind of the droplet formation will be there, but this can be considered as independent of the modeling approach, means what are the temperature distribution and flow field, that is independent of the condition for the metal transfer mechanism associated with this particular process. So, some sort of mathematical criteria may be needed to set for the transition from the globular to the spray type of the metal transfer, and that can be represented as a function of welding current, but this can be set. So, do some kind of the simple analytical calculation we can follow, and this condition can be obtained from this particular analytical solution. So, what kind of the metal transfer there, or if there is a transition from the one kind of the metal transfer mechanism to another thing. Point is that this condition for the different kind of the metal transfer mechanism is we assume the independent of what the modeling approach or maybe modeling approach means the what we are solving the heat transfer and fluid flow phenomena associated with this particular problem. Now, suppose this is the actual domain of the analysis. So, now we have to look what are the different domains. So, you can see there are the two different kinds of the domain. One is the metal domain, maybe we can consider the metal domain, that means from the electrode as we can start from this point. So, there is a starting the formation of the droplet. Now, droplet is growing over as a function of time. So, droplet is growing over as a function of time. So, once particular size arises and there is a balancing effect of the other driving forces for the detachment of the droplet, and then one particular timing, say a droplet can grow from very small to little bit bigger, but this normally happens over a finite time. Now, then put some analytical criteria to detachment of the droplet from the electrode. So, that is also time phenomena. Now, droplet detachment happens one particular time t. So, say for example, t equal to 0 and t equal to t1, with this particular time droplet is detached, and say this is the workpiece. Now, droplet is transported. So, for example, there is a change of the shape when in this particular position, say t equal to t3 in this particular situation. Now, when it is touched to the workpiece and becomes part of the finally, first it will touch to the workpiece and then molten becomes part of the workpiece material. So, then suppose we count t equal to t4. So, these are the at the different time phenomena we can track how the molten this kind of modeling can be done from here to reach the becomes final part of the workpiece. So, in that cases to do this kind of analysis, maybe it is in the form of a mathematical model development is quite complex. Then we have to look into that. One approach can be like that. Maybe we can track what are the droplet creation, and the droplet becomes final part of the workpiece material. So, this is the one domain, metal domain, from the electrode tip to up to the transport to the workpiece. Now, there is another domain also. For example, the analysis something like that. So, this is suppose this is the initial shape of the workpiece. Now, there is a droplet transported. So, droplet just touch into this workpiece. Now, that means this once touched to the workpiece, there is a addition of the mass to the domain only which we are focusing only on the workpiece. So, then it becomes part of the workpiece and it basically mixes with this thing, and droplet becomes spread over the workpiece surface. So, this how from the touching point to the spread over the droplet over to the workpiece, during that time period we can make the model also, even one touching to the workpiece, and then we can follow further when spread over the workpiece, and then how the solidification or maybe the cooling phenomena happens associated with this process. This whole phenomena can be captured during this process also, but in this case definitely there is addition of the mass to the workpiece domain. So, this way we can track how the droplet transported to the workpiece, and the second part of the solution domain only on the focus on the workpiece, and then we can analyze the workpiece, and that means with the if addition of the particular droplet, what may be the free profile can be obtained on the workpiece. So, this is the another domain of the analysis. So, this way we can divide the different domain subdomains, and within this different domain subdomain we can solve the governing equation associated with this thing. For example, if it is considering only on the heat transfer part, then we can solve only the heat conduction equation during this particular process, maybe at the defined geometry or the defined boundary interaction. Then if there is a need to look into what are the material flow field also, then we can solve the Navier-Stokes equation or the fluid flow field we can estimate along with the boundary condition. Apart from this thing, if we want to track what are the free surface profile of the droplet, as well as the when droplet is transported to the workpiece, what are the free surface profile of the workpiece. To look into this surface profile, then we have to look into some kind of the interface tracking method to understand how the shape of the droplet or shape of the workpiece normally happens during this particular process. So, this way we can analyze this thing looking into the different domain, or what kind of the governing equation has to be chosen, what kind of the boundary condition has to be there, that you have to look. But apart from this thing, since this particular domain under there is a flow of the current, so definitely it is associated with some sort of the magnetic field. So, in this case maybe this whole domain is basically affected by the magnetic field. This then we have to consider the magnetic, we maybe consider the magnetic field. For example, this magnetic field is not affected the only the heat transfer analysis, but magnetic field is, it normally affects the fluid flow phenomena. So, in that case we should know the magnetic field can be act as a body force when you try to solve the Navier-Stokes equation to understand the material flow field. In that cases, this magnetic field can be act as a body force for the solution of the Navier-Stokes equation in this particular process. So, in that cases the magnetic field will come into the picture. So, that is another aspect to look into, but that can be incorporated. First is the first magnetic field potential equation has to be solved, and from there we will be able to predict what is the magnetic field in this particular process. And of course, magnetic field is basically driven by the current density distribution also. So, then once we get the magnetic field, and that can be considered as the input as a body force for the solution of the momentum equation, and that will impact on the flow field in this particular process. So, that is also there. So, there is a complex interaction of the different physical phenomena associated with these things. This is the one aspect. Another aspect is the, if you see, there is a arc. So, arc, what are the distribution of the arc? Arc is the different medium. So, different medium, even we can follow the momentum equation also, and we can predict the potential lines of this particular arc. The flow field also can also be possible to solve in this to represent the arc, only for the arc. Now, apart from the arc, there must be, it is associated with, we are not showing here, it is associated with some sort of the shielding gas also. So, shielding gas is also interacting in this thing. So, flow of the shielding gas can also be modeled simply by solving the momentum equation also. Then we can predict the flow field in case of by using the shielding gas, because this arc pressure and this thing and the flow field that by the shielding gas, that actually influence the free surface profile on the workpiece surface. So, here this free surface profile, when droplet is interacting on the workpiece material also, then what way the free surface profile will be generated in this particular interaction, that is influenced by the arc pressure also, at the same time the shielding gas pressure also, the flow field by the shielding gas, all actually influence the free surface profile on the workpiece. So, therefore, this analysis, the separate analysis of this distribution of the flow field in case of the arc as well as the shielding gas is also required. Of course, there is interaction of the shielding gas and this arc also, but maybe we can neglect this thing, then modeling approach becomes more complicated in this particular situation. So, let us look into this thing, the simplified way what we can do the modeling approach. So, already we have we explained this thing, for example, where feed rate is there, and for example, the one thing is that suppose this is, we can consider this as a subdomain. So, subdomain is something that this is the some part of the solid wire is there, and then at the tip there is a this formation of the droplet, and then that between the electrode and the droplet there is a solid liquid interface is there. Now, this we can do conduction analysis, and this in this case in this particular domain, and this domain is basically associated with some sort of the different medium, and the gas medium is there surrounding this particular part. So, therefore, up to the detachment of the droplet, so droplet form and then grow, this we can do simply the temperature analysis. That temperature analysis means when it is hitting the critical temperature. So, say assuming the melting temperature, then droplet start forming. Once droplet start forming, then once it is a liquid state, then we can start within the droplet also we can start forming the flow field also. Apart from this temperature field, we can estimate what is the flow field. Now, this flow field is influenced by the different driving forces for the detachment of the droplet. So, once we estimate the flow field from using the different detachment of the droplet, then we can find some kind of the condition also that detachment of the droplet occurs. So, once detachment of the droplet occurs, then we can look into the another subdomain. So, subdomain 2 we can consider. So, then droplet under the electromagnetic field, see droplet becomes under the electromagnetic field is there, shielding gas also there, and plasma arc and the gravitational field all is acting, and there may be some other driving forces is acting. Now, this one detachment of the droplet happens, then we can consider this is a separate domain. For example, it starts at this point detachment of the droplet happens, and this to before touching the workpiece up to that part, we can consider the another subdomain too. So, then within the subdomain there may be change of the shape of the droplet. This is under the influence of the several driving forces, for example electromagnetic fields, even the shielding gas environment, even arc pressure also, all actually act here, even gravitational pressure is also there. So, therefore, what we can do in these cases, we can do maybe only the thermal analysis, that means temperature, as well as the flow field also we can estimate. And then apart from this thing, we can add the any surface tracking method also, such that we will be able to predict what is the free surface profile for this particular droplet. So, all these things are there. So, it is a temperature plus flow plus interface tracking method. So, all these three phenomena has to be considered to look into the actual shape, their temperature distribution, and the flow of the material within this droplet, that can be able to predict these things. So, this is the subdomain 2. Now, we can consider this as this is domain 1. Now, this is the one part up to this part, this is, we can divide the domain 1 and the subdomain within the domain 1, there is a subdomain 1 and subdomain 2. And this other part is that other computational domains. So, for example, this is touching to the workpiece, and this touching to the workpiece, and there we can consider only the metallic domain, but this metallic domain is the metal domain, such that will be only the purpose of this thing when touch the droplet transfer to the workpiece, then what can be the free surface profile, and that is more important, because we will be able to know what is predict the free surface profile, which may be helpful to gain the information in case of the metal printing technology development. So, therefore, in this computational domain touching the workpiece, but this everything happens under the influence of this arc, maybe free surface profile, we can consider this as a up to this as a computational domain, and then we can predict the free surface profile under the influence of the arc pressure and this thing, this electromagnetic field and the arc pressure, or maybe the flow field of the shielding gas. Within that, this domain is transported to the workpiece. So, then here we can predict the free surface profile using this particular domain. But of course, here in this particular domain, this once it this thing we can look into the heat transfer, mainly the heat transfer analysis, and the heat transfer analysis as well as the fluid flow analysis for this domain, because this is already molten state. So, fluid flow analysis and plus the interface tracking when droplet is basically becomes part of the workpiece. So, all this kind of the analysis is possible this thing, but once we do all this analysis and even we want to apply some kind of interface tracking method also, then it is necessary to fix the domain. For example, assuming some size of the droplet, so droplet touching this to workpiece, so we can fix this as the computational domain, and within this computational domain we can do the analysis of the temperature distribution as well as the flow field, but only this computational domain, but flow field and free surface field, but it is associated only with the metallic domain, only the metallic component part. So, we can exclude here the what is the effect of the analysis for the gas and the arc also, that part we can exclude, but the shielding gas distribution, their distribution, their flow field, and even arc pressure, basically arc formation, their domain of the arc, that can be done separately. That is the different domain, the apart from the metallic domain. Here droplet addition, here also computational domain 2, I have already explained this thing. Computational domain, if you see, it is under the influence of the plasma, maybe under the influence of the plasma or under the arc, then boundary interaction, addition of the liquid droplet to the another molten pool, and this is the solid workpiece. So, here start with this thing, then gradually over the time how the free surface profile evolves, that is the final objective of this particular computational aspect. Now, if you look into overall this thing, see in gas metal arc welding process and metal transfer part, then we see that constant wire feed rate is there, always there. This is the creation of the arc, molten droplet formation, then free surface profile of the molten droplet, and the molten droplet formation is there at this particular point, and only the heat transfer is there. Then electromagnetic field, it is acting, the electromagnetic field is acting these things, then electric arc will be created here, and then after that droplet interaction, droplet transported, and then interaction with the molten pool happens, and then this is the solution domain, means this is also solution domain, this is also solution domain, but we have already explained that we can divide the different domains. But this is within this we can do the heat transfer and the material flow, but this is the solid workpiece. So, only heat transfer equation has to be solved. So, this way if we physically understand what are the different phenomena is happening, based on that we can decide which governing equation has to be solved one particular domain. So, if you look into overall all these things, making in a single domain and analysis all these things in the different part is really complicated, it is very difficult or almost impossible. So, rather we can divide in the different domain, and then we can do the analysis, and of course, once we do the different domain and then interaction, maybe some strategy how we can interact from thermal model to the fluid flow analysis, or how we will interact magnetic field to the fluid flow field. So, that has to be incorporated, because you have already seen this thing that when you solving the governing equation as a heat conduction equation, there is a heat generation term is there. So, that is internal heat generation term. So, sometimes the thermal phenomena, all this thing can be incorporated through the internal heat generation term. If there is a fluid flow phenomena, there is a scope to incorporate the body forces. So, maybe other driving forces can be incorporated through the body forces, or driving surface tension forces can be incorporated through the surface forces in the governing equation, or that can be surface tension force, or maybe other surface force acting during this fluid flow model also, that can be incorporated through the in the form of a boundary interaction. So, all this interaction phenomena has to be considered, and then you have to choose the basic governing equation to solve, then we will be able to solve this kind of the complex problem. But definitely finally we can say that it is better to solve all this phenomena by dividing the different computational domain and then solve for the different kind of the domain. Now, if we look into the in modeling approach, what are the different governing equation is normally used in this particular domain, that with some idea this thing. First is the governing equation, this complete problem associated with the metal transfer in the gas metal arc welding process is that continuity equation. First need to solve the continuity equation, then momentum conservation equation, we have seen already the momentum conservation equation, and then we can see the momentum conservation equation, this is the shear stress is there. So, in this shear stress maybe we can look into either surface tension term, or the surface tension can be incorporated through the boundary condition. Here it is associated magnetic field current, basically the current density and magnetic field is associated here, and this is the other driving forces maybe in the fluid flow phenomena, the other driving body forces that can be incorporated here in the fluid flow phenomena. We have seen the momentum conservation equation. Now, energy conservation equation we can see, against the energy conservation equation we can see it is associated with the electrical conductivity, and then J is the current density. So, electrical conductivity and current density is associated, that can be the energy conservation equation in terms of the heat generation term, and we can see the other term also there. This is also Boltzmann's constant. So, this is radiative emission, though actually the radiative emission all this thing, and that electrical, how the electrical field is interacting also, that there is a scope to incorporate all this thing in the energy conservation equation as well. So, but all these phenomena in these cases it depends on the current density. It is simply how what we can incorporate in or interacting the magnetic field or the current density, that particular current density distribution in the governing equation, that can be, that you can see also that they are having some influence in the energy transport, and that is why we can incorporate all these things. So, definitely apart from this thing, this is the welding velocity, V is the welding velocity, and E is the electronic charges. So, because of the electric field then presents this thing, there may be some sort of the heat generation, and that we can incorporate in the energy conservation equation apart from this radiative heat transfer as well. So, these are the governing equation that if we solve this governing equation, we will be able to know that solving the basically this temperature distribution, that velocity field U, V, W is a 3 dimension, this is the velocity field. So, this kind of information, and apart from this thing we will be able to get the pressure field also. Pressure, because Navier-Stokes we can see the momentum equation, it is associated with the pressure. So, these are the output from this particular governing equation, but you see whether these are the output from this governing by solving this governing equation, but how there is interacting of magnetic field also there. So, that different way we can incorporate the effect of the magnetic field in this particular governing equation, that we have shown here also. Apart from this thing, electrical, now what we can estimate the magnetic field also. So, electrical potential and magnetic field, what we can get this kind of information, because in that cases current continuity equation has to be solved. You can see the current continuity equation has to be solved here, and where the current density is related to the electric potential is this J current density in terms of the electric potential, we can incorporate that there is a relation between these two. And apart from this thing, B is the magnetic field strength, and magnetic field strength B is the magnetic field associated with the magnetic potential vector. So, A is the magnetic potential vector, and magnetic potential vector is associated with the current density, and mu 0 is the basically magnetic permeability of the free space. So, it means that electrical potential and the current continuity equation has to be solved here to get the magnetic electrical potential field. So, phi electric potential field we need to get first. So, once we get the electric potential field from there and electric potential field from there, we can estimate what is the current density also. We can link between the current density, and then current density, from the current density we can estimate the magnetic field. So, basically need to necessary the electric potential field as well, and from there we can estimate what is the magnetic field existing during this particular process. So, in these cases we need to solve all this kind of the equations, and then we have to understand that how one equation is linked from the another equation. If you solve it, we will be getting all this phenomena. Now, apart from this thing, one say, so these things are basically then we can get the magnetic field distribution also, but this magnetic field distribution also, this information is also necessary to solve the governing equation, for example, conservation of mass, movement of energy equation. There is a need the input from the magnetic field also. So, that will help in this particular case to get this pressure, temperature, and this thing, the velocity field. Apart from this thing, we need to solve the free surface profile and the surface tension. So, basically we have to understand how the surface tension force is acting there, and then from there we can estimate what is we can develop some model for the free surface profile. We have already explained the different interface tracking method also, but we have to adopt this interface tracking method, and such that we will be able to predict the free surface profile. So, therefore, we can look into there is a complex approach there to get all this kind of the flow field. Now, if we look into this thing modeling approach of gas metal in a nutshell, like that computational domain is the divided into the different either divided into arc domain. Arc domain means the arc column and the shielding gas. So, that we can consider this as arc domain, and the metal domain another separate domain, that is called detach the droplet and the workpiece. This we can consider as a metal domain, but there is a several subdomain can be created within the metal domain also. Now, for current distribution, we can solve the current continuity equation this thing, and magnetic field equation are solved in the entire computational domain. So, if you know the current distribution, therefore, current continuity equation and magnetic field equation has to be solved for the whole domain. And then in this case, we have seen the primary variables, the U. So, pressure and the velocity component and temperature are basically that is required to calculate separately in the metal domain only, in the metal domain and the arc domain, because arc domain this pressure distribution, velocity field, temperature domain also we can estimate, because this domain medium is different as compared to the metal domain or metallic material. So, therefore, in metal domain the arc region considered as a void. Once we look into the metal domain, the arc region is considered as a void, or in the metal domain we are looking into this thing, depending upon this thing we can estimate what is the flux, volumetric flux associated with this thing. That volumetric flux can be incorporated in the energy conservation equation or momentum conservation equation, and there that can be input as in terms of the body force in both the equation, and the equation can be solved for the more precisely can be solved for the prediction of the velocity field and the temperature field. Now, two domains are coupled through the interfacial boundary condition. So, definitely it is also possible the two domains, that means the arc domain and the metal domain can be coupled by interfacial boundary condition, because these are the two different medium. We can see this is a kind of a gaseous medium, another is the kind of liquid medium, or we can say the liquid medium and the gaseous medium. So, in between there is interface. So, that interfacial boundary condition can be imported in this particular solution. Now, VOF means volume of fluid method can be used in the solve on the metal domain, basically to track the moving free surface of the electrode, that we can see the moving free surface of the electrode and the moving free surface of the droplet, and the weld pool with the free boundary conditions set at the metal surface. Basically, we will be able to predict the weld pool profile also using the volume of fluid method. So, volume of fluid method is simply the one of the interface tracking method that we can apply to look into the different shape and size of the droplet, and as well as the free surface boundary of this particular droplet. So, these are the in general the overall approach of in case of the metal transfer associated with the gas metal arc welding process. So, analysis of this particular approach or maybe in the modeling approach is basically helpful or applicable when you try to develop some kind of the wire arc based additive manufacturing processes. So, thank you very much for your kind attention.